this is my lab report for circuits. So the purpose of this lab was to use the principles of energy and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. So the main results was that delta V for the round trip was 0, the 20 ohm light bulb took longer to dim than the 10 ohm light bulb, and my RC value was 6.072 seconds. So physical principles to understand for this lab is that current in series is the same throughout the entire circuit, so I1 is equal to I2 for however many resistors are present. And then Ohm's law, we need to know that voltage is equal to I times R, where I is the current and R is the resistance. And then the trend of voltage difference over time of a capacitor was given in the lab experiment guide. And then we also need to know Kirchhoff's loop rule, which states that the round trip potential difference is going to be 0 in a closed circuit. So for the first experiment, we had a series circuit with two 1.5 voltage batteries, 2 ammeters, and then a 47 ohm resistor and a 100 ohm resistor. And in this one, we kind of were just predicting what we thought the value of I was going to be, which I got to be 0.02 amps, and I confirmed this reading with the ammeters on the simulation. And then we also recorded the delta V at different points along the circuit path, and here is a graph showing that here. As you can see, it starts at 0 and ends at 0, which confirms the Kirchhoff's rule. And then for the resistance calculator, I took the delta V given from the voltmeter for each for the 47 ohm resistor and the 100 ohm resistor, and I ended up getting 48 ohms and 102 ohms. So I attributed the difference between the calculated resistance and the known resistance to rounding on the simulated ammeter and voltmeter, because it rounds to like 1 sig fig on the ammeter, so it's less accurate, and we found that the resistance for the wire and ammeter were both negligible. So for the RC circuit, the first one, we charged a capacitor with while it was connected to a 10 ohm bulb and a 9 volt battery, and then we also repeated it with a 20 ohm light bulb, and we also measured how much time it took to discharge it. So for that, I found that the 10 ohm bulb took 15.5 seconds to charge, and the 20 ohm took a little less than twice that, and then for it to discharge, the 10 ohm bulb took 19.6 seconds, and the 20 ohm bulb took 39.5 seconds. And here's just showing, like, prior to charging and prior to discharging, the light bulb was both very bright, and then after charging and after discharging, the light bulb was completely dim, and you can see that here the capacitor is charged and here the capacitor is also charged. So for the main part of the lab, the RC circuit, measuring the voltage versus time, so we built a circuit with a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm light bulb, and this is going to be the main system, and then the surroundings, everything else, and we're assuming that the resistance in the wire and capacitor is negligible. So we set up a circuit in series with a 9 volt battery, the capacitor, and the light bulb, like I said, and then we measured the voltage across the capacitor using a voltmeter, set it to discharge, and we recorded at least 20 seconds of voltage versus time data, and then we calculated RC using the plot. So my found results were that my RC was 6.072 seconds, and the expected RC value is about 6 seconds, so it's pretty close. Here you can see my graph here, and what my voltage readings were at. I just did 5-second intervals, and then I plotted it, and as you can see, RC is equal to 6.072 seconds. Sources of error, so as I mentioned before, discrepancies between known/given values and calculated values can be attributed to rounding on the simulated ammeters and voltmeters, producing less precise results. And then for the RC circuit portions of the lab, errors can be due to issues with timekeeping, such as not starting the stopwatch at the exact same time as starting the circuit and not measuring at exact time points. So if I say it's a 5-second reading, but it might actually be like a 5.6 second reading. For the what-if questions, so if we were doing this in real life and use an actual ammeter instead of a simulated one, the current that's measured would be lower because real ammeters have non-zero resistance, whereas the simulated ammeters have negligible resistance. So because current and resistance have an inverse relationship, the measured current would decrease as the resistance increases. And if we used a real battery and a real capacitor for the charging capacitor experiment, ideally we would want the capacitor to be charged almost instantaneously, which is reflected in the experiment that we did, as the time taken was within seconds to fully discharge or charge. But in real life, the wires and capacitor both have resistance, which would delay the time taken to fully charge the capacitor. Thank you.